Hello, my name is Anshukumar Maitra, and this is video number 4 for ME210, Impulse and Momentum. This video that I have shown below is from the Insurance Institute for Highway Safety, or IIHS for short, and they are testing different cars and grading them based on how well the car can protect a driver in a crash. And here's a clip of the video below. Using a segment of the video from IIHS testing a Mazda CX-30, I have created the following problem statement. In this IIHS crash test, a Mazda CX-30 is traveling at a constant speed to the left when it collides with a barrier. What force in newtons must the barrier exert on the car in order to bring it to a stop in 0.5 seconds? Some necessary assumptions that we must make to solve this problem are that the mass of the car is 1,500 kilograms, the initial speed of the car is 60 kilometers per hour, both the barrier and the car are rigid and don't dissipate forces when they collide with each other. The final velocity of the car is 0 kilometers per hour. There is no air resistance or friction acting on the vehicle. The car only moves in one dimension, which is only in the x direction, and the car doesn't lose mass after the crash. Here are some key concepts and key equations that we must apply to solve this problem. The first key concept we need to know is that this is an impulse and momentum problem, so we need to apply the impulse and momentum theorem, which states that the initial momentum plus the impulse on an object is equal to the final momentum of the object. And the second key concept is that the impulse is equal to the change in momentum. And the third key concept is that momentum is equal to the product of mass and velocity. The key equations that we need to apply to solve this problem are that mv1 plus the integral of f from 1 to 2 dt is equal to mv2. And the second key equation is that the force times the change in time equals the mass times the final velocity minus initial velocity. And the third equation is the momentum equation, which states that rho equals m times v. Finally, to actually solve the problem, we need to draw a sketch, free body diagram, and inertia diagram. For the sketch, we have the car and the barrier, and the car is initially moving to the left at 60 kilometers per hour, and the mass of the car is 1,500 kilograms. The free body diagram shows that there is a normal force and force of gravity acting on the car in the y direction, and in the x direction, there's only the force by the barrier on the car at the instant the car hits the barrier. And in the inertia diagram, there is only one inertia force, which is m times the acceleration in the x direction. And the axes that we need to solve this problem are that the positive x is to the right and positive y is straight up. But for this problem, we don't need to worry about the y direction since the car is only moving in one dimension. And I have also listed the 3 equations that we need to solve the problem below. But to actually solve the problem, we only need to use the second equation and divide by delta tide. So we get that the force is equal to the mass times the final velocity, which is 0 kilometers per hour, minus the initial velocity, which is negative 60 kilometers per hour. And then we need to divide it by delta time, which is going to be 0.5 seconds. But to make sure that the units match, we need to convert that negative 60 kilometers per hour, that initial velocity, to meters per second. So all the units will match and we can get the final force of some amount of newtons to the right.